Swayam Prabha. Digital India. Educated India.
Welcome to another lecture on Introduction to Machine Learning. Today we will talk about mathematics of machine learning. Here we will build the mathematical foundations that you will need to understand machine learning models, to express them in a mathematical way and see how machine learning algorithms work. Specifically, we will be looking at vectors, matrices and calculus which are part of linear algebra, and then we will also be looking at convex optimization, which will be used for training machine learning models, and then we will be looking at probability distributions. So first let's revise what are some scalar and vector operations. So as you know that a scalar is a quantity of one dimension. So let's say you have a scalar A. Okay, the way we represent it is that A belongs to set of real numbers, and we will write that as stylized R. Okay, so it's a single dimensional entity. So this could be a negative number or a positive number. Now compare that to a vector. So I will use this line on top of the vector, but in mathematical notation you would be using a bold X if you were to be typesetting this, and this will belong to a multi-dimensional, this is a multi-dimensional variable. So let's say its dimension is n, so it will be n cross 1. So an example is that you have x, which is a vector of 3 numbers, 100, minus 100 and 22. Okay, so this is let's say we call each of these dimensions as x1, x2, x3. So we will have x1, x2 and x3. Okay, so this belongs to the set of real numbers with dimension 3. So 3 cross 1 or 3, we can simply write R3. Okay. So this is how we will represent vectors and scalars. Now these vectors and scalars, they can be in multiple operations together. So for example, we could multiply a vector and a scalar. So we would usually write the scalar first and then the vector. So Ax, for example, will scale all dimensions of x by a factor of a. So this would be equal to, let's say if x was x1, x2, x3, then you would have Ax1, Ax2 and Ax3. So all 3 dimensions are scaled by a factor of a. Now we can take this vector x, but we cannot add a scalar to it a. This is not an operation in linear algebra, but in many programming languages this operation is given. So for example, in NumPy library of Python, this operation is well defined. What this simply means is that you would, so it's an abuse of notation, it's not there in linear algebra, but in programming this convenience has been given, where you would simply add the vector a, the scalar a to all dimensions of x. So if we were to write this in linear algebra notation, then we will not write it like this. Instead, what we will write this as is this vector x plus a times a vector of 1s, which we will write as this stylized 1. So now you have x1, x2, x3 and that vector is added with a times a vector of ones. Okay. So these two are equivalent. One is in programming notation, the other is in actual linear algebra notation. So that is because we want to have a dimension matching when we are adding two quantities. So we cannot add two quantities unless this dimension is also n cross 1 and this dimension, the dimension of this vector is also n cross 1. So this brings us to the next set of operations that you should be familiar with. These are vector operations. So let's say if we have two vectors x and y, okay, these two can only be added if they both have the same dimension. So for example, this has to belong to r to the power n and this also has to belong to r to the power n. If one of them has a different dimension, then this operation is null and void because we would not know what to do with the mismatching dimensions. So if we were to add these two, then this is simply, let's say if these were both two dimensional vectors, so it would be x1 plus y1 and x2 plus y2. Okay. The next vector to vector operation is the dot product. So you have x dot y. It is also written as x transpose y, okay, and it is also written as angle bracket x comma y. All three mean the same thing, and basically what this means is we take a sum product of the corresponding dimensions. So this would be x1 y1 plus x2 y2, and if we had three dimensions then it would be plus x3 y3 and so forth. So how this comes about is that if we look at the dot product, the transpose of x is obviously x1 x2 as a row vector instead of a column vector. So now this belongs to r to the power 1 cross 2 instead of a 2 cross 1, and then we would take a multiplication of this with y1 y2, and as we multiply matrices of two different dimensions, one is of dimension 1 cross 2, the other is of dimension 2 cross 1. So we would get a quantity that is of dimension 1 cross 1, which is a scalar. So this is a scalar. Okay. In machine learning, we would use another operation which is an element wise product of two vectors. So let's say if we have x1 x2, okay, we would take its element wise, usually represented by a dot and a circle around it, and y1 y2, and these two vectors also should have the same dimension, and the resultant would have element wise product. So we will have x1 y1 and x2 y2. Okay. So this is the third operation that you should know about. So again, this has to be n cross 1, this has to be of dimension n cross 1, and the resultant also has dimension n cross 1. Now, next thing that we will talk about is subspaces that are spanned by vectors. First, let's talk about what is a vector space. So let's say we have a set of vectors V, this is a big V, this is a set which contains many vectors, and let's say we have for all V1 and V2 that can belong to this set, if two conditions are satisfied, then it is a vector space. So, what are those two conditions? The first condition is that V1 plus V2 should also belong to V. It should belong to the same set. The second condition is that if I scale V1 with a scalar, then that will also belong to V. Okay. So, if these two conditions are satisfied, then we will call V as a vector space. Now, if we have a subset of this, so let us say we have two vectors W1 and W2, okay, that belong to a set W, which is a subset, okay, of V, okay, and this set W is also a vector space, then we say that W is a subspace of the vector space V. So, which means that this should also satisfy W1 plus W2 belongs to capital W, and any constant times W1 also belongs to capital W. Okay. So, in that case W is a subspace of V. So, an example of this would be that let us say we have two dimensional vectors, a two dimensional vector space, and this vector space has you have any vector which is which has dimensions x and y, right. So, let us say you have a vector V here which has Vx and Vy, but now if I take a line, let me change the color of the pen. If I take a line that passes through the origin, and all the vectors that I have, they can only lie on this line. So, this line is a subset of the plane in the two dimensions, but then any vector that lies on this line, if I add them up, they will still lie on the line. If I scale them with a factor c, then they will still lie on the line. So, in that case they are so this line could be the vector space W, whereas the two dimensional space that we had would be the vector space V, and this W is a subspace of V. So, what do we mean by spanning subspace spanning vectors? So, for that I will have to go to 3 dimensions. So, let us say we have a 3 dimensional space, okay, and I take a plane that is passing through the origin, okay, and I take all the vectors that lie on the plane that passes through the origin. Then if I take any two vectors that are lying on this plane, so long as they are not collinear vectors, so long as there is a non-zero or non-180 degree angle between them, I can reconstruct any vector that lies on this plane with these two vectors. So, let us say these two vectors are W1 and W2, then I can have alpha 1 times W1 plus alpha 2 times W2 will give me any vector that lies on this plane. So, then W1 and W2, as long as they are not collinear, that means one is not just a scalar multiple of the other, then these two vectors will span the entire subspace which is capital W. Now, let us look at some matrix operations. So, for matrices I will use a capital X with a bar on top, it is actually bold X, and I will also use capital Y similarly. So, let us say you have two matrices X and Y, okay, and they both belong to the set of real numbers with power m cross n, okay, which means that their structure would be something like this, that they will have m rows and n columns, okay, and any particular element is xij is at the ith row and the jth column. Okay, so that is the structure, and this is the notation of the set of matrices that have dimension m cross n. So now I can represent their sum, okay, which would be an element wise sum. So basically I will have any particular element would be xij plus yij, okay, and on the top left I will have x1 plus y1, etc. This is not angle bracket, this is a regular parenthesis. Okay. So I can only add two matrices if they have the same dimensions, both have the same number of rows and both have the same number of columns. I can also take their product, but then they should have a structure that is slightly different. So if I take the product of matrices x and z, and this belongs to r to the power m cross n, then the z matrix should belong to r to the power n cross p, so that the number of columns here matches the number of rows in the next matrix. So now this, if p and m are not the same, then I cannot actually exchange it. I cannot do z times x. I can only do x times z if only the number of columns of x match with number of rows of z. So this would be simply taking the entire row of x, first row of x, multiplying it, taking its dot product with the first column of z. That is why the dimension n has to match. Okay, so your top left element would be x11 z11 plus dot 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 x1n times zn1. So this would be your top left column, and similarly you will have all the other elements which would also be sum products, which would be basically dot products of the rows of x with columns of z. So this product will belong to the set of real to the power m cross p. Okay, so it will have m rows and p columns. Now, similar to how we defined an extra operation for vectors, which was an element wise product, we will also define that for matrices. So we have x and its element wise product with y, and here both of them have to have the same dimension. So if this is m cross n, this y also has to have dimension m cross n, and what we have is simply an element wise product, which would be x11 times y11 here, all the other elements, and the last one would be x mn times y mn. So this also belongs to r to the power m cross n. Now let us look at some other properties of some other operations on matrices, including its transpose, determinant and inverse. So let us start with transpose. So if you have a matrix X, okay, and you take its transpose, then the rows becomes columns and the columns become rows. So basically what we will have here, so if X belong to r to the power m cross n, this will belong to r to the power n cross m. Okay. and we will have x11, the position of x11 will not change, but now instead of all the way down having xn1, we will have x1n, okay, and all the way here we will have xm1, and all the way here we will have xmn. So these two corner elements, their position doesn't change, everything else flips around basically their rows and columns get exchanged. Okay. Now if you have a square matrix, so a square matrix would be, let's say, x that belongs to r to the power n cross n, then we can compute a quantity, very important quantity for this, which is called its determinant. So for a 2 by 2 matrix, so let's say if x is equal to a, b, c, d, okay, then the determinant of x, okay, would be the product of AD minus the product of C and B, AD minus BC, okay, and this operation to compute this scalar, which is the determinant of x, can be extended to 3 by 3, 4 by 4, any n cross n matrices. Okay. Then for certain matrices which are square, matrices, we can define an inverse of that matrix under certain conditions. So let's say if I have the matrix X which belongs to r to the power n cross n, then we will define another matrix which is also having the same dimension n cross n, and their multiplication would be the identity matrix in n cross n dimension again. So which is basically you have diagonal elements are all 1 and all the other elements are 0. So it's like the multiplicative identity in matrices. Okay. So why do we say that not every square matrix has an inverse? We will see that the rank of the matrix has to be full rank, which means it has to be n for this inverse to be well defined, otherwise we cannot define this inverse. So for square matrices, for 2 by 2 square matrices, the simple answer for x inverse is going to be, so by the way, this is also denoted as x with the modulus sign. So 1 by determinant of x, okay, and then we will have d minus b minus c and a. Okay. So let's take an example. Let's say x is equal to 1, minus 2, 3 and 4. Okay. Then the inverse of x will be x inverse will be 0.4, okay, 0.2, minus 0.3 and 0.1. So what is the determinant? Determinant is 4 minus 6, which is 10. So that's where we have 1 by 10, and then d minus b minus c minus a becomes this, because these are all these numbers, these same numbers divided by 10, and you can see that if you multiply these two matrices, you will get an identity matrix in of size 2 by 2. So, now let us talk about what is the rank of a matrix. So, the rank of the matrix, simply put, is the maximum number of rows or columns that are linearly independent of each other. Let us take some examples of what that means. So, let us say you have a matrix which is not a square matrix, but it is a rectangular matrix. So, let us say it is 1, 2, 3 and 4, 5, 6. Okay. So, the maximum number of rows or columns is 3, but the minimum number is 2. So, now what we can see is that this third column can always be represented as some linear combination of column 1 and column 2. Okay. So, I can take alpha 1 times column 1 plus alpha 2 times column 2. I just need to determine what is alpha 1 and alpha 2, and I will get column 3. So, which means that the third column is not independent of the other two columns. So, although this belongs to r to the power 2 by 3, the maximum rank that this matrix can have is less than or equal to 2. So, basically your rank of matrix X is less than or equal to minimum of n and m. Now, let us take an example where the rank is even lesser than 2 for a matrix that is of size 2 cross 3. So, let us take the matrix Y, okay, and let us see if we have 1 4, 2 8 and 3 12. So, here just a single column, if we multiply it with some scalar, I can get the second column, I can get the third column by multiplying it with another scalar. So, here the rank is going to be 1. There is only one independent row or column. Okay, so, this is the less than condition in that less than equal to that you saw above this. So, such a matrix which has a rank smaller than expected is called a rank deficient matrix, and that is usually it applies to square matrices, rank deficient matrices. Okay. So, where the rank is less than the full rank that is expected. So, if you have a 2 by 2 matrix, so let us say your X was 1 4 2 5. So, this is full rank because the expected rank is for a general 2 by 2 matrix is 2, and it has that, it satisfies that. But if we had 1 4 and 2 8, then this would be rank deficient. So, we saw the inverse of a matrix, we saw rank of a matrix. Now, let us talk about pseudo inverse of a matrix. Pseudo inverse is a type of it is another matrix that we compute from starting from any matrix that can produce, that can be multiplied with rank deficient matrices to give you to give you an identity matrix. So, it is not a real inverse, it is a pseudo inverse. So, let us say you have a matrix X, and this need not even be a square matrix, okay, and I want to multiply it with some matrix such that I get an identity matrix. Okay. So, I will multiply it with a matrix called X, this pseudo inverse, and the definition of this is that you take the conjugate transpose of X, this is conjugate transpose. So, what is a conjugate? Basically, you are taking if the elements of the matrices of this matrix were complex numbers, you would invert the sign of the imaginary part, and then you would take the transpose, which means you would exchange the rows and columns, okay, and you would multiply it with x. Now, this product, even if x is not a square matrix, this will be a square matrix, and we can take its inverse, okay, and then multiply it with x, conjugate transpose again. So, now if you multiply this matrix with x, right, you will get an identity matrix. How? So, basically your x plus times x is equal to, by definition, x plus is x conjugate transpose times x inverse x conjugate transpose, right. So, this whole thing times x. So, now you can see this group and the inverse of this group, and you would get an identity matrix. So, here this could be of size m cross n, and obviously your conjugate inverse is of size n cross m. Okay. So, when you multiply both of these, what you will get is equal to I, which is in n cross n. Now, let us look at another property of square matrices, which is eigen decomposition. So, let us say you have a matrix A. Let us say you have a square matrix A, which is of dimension n cross n. Okay. If I can find a vector V such that when I multiply this matrix with the vector, so this vector is of dimension n cross 1. If I multiply them, I will get a vector of size n cross 1 again, and it turns out that it is basically a scalar times the same vector. Then what we call is that V, the vector V, is an eigenvector of A, and lambda is eigenvalue of A. So, these basically characterize how the some important modes or directions that the columns or rows of the matrix have, which we will see when we get into principal component analysis in machine learning. So, here in general, if you have a square matrix n cross n, it will not just have a single eigenvector and a single eigenvalue, but it will have n different eigenvectors and eigenvalues which will be paired. So, I belongs to 1 dot 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 n. Now, if A is a rank deficient matrix, then some of these eigenvalues will be 0. So, if the eigenvalues are 0, that if you have n non-zero eigenvalues, that means that your matrix A is full rank. So, the other interesting property of this matrix A after eigen decomposition is that if I take this matrix A, I can represent it as a product of three matrices. One is, let us say, Q, the other is lambda, and the third one is Q inverse or Q transpose even. Okay. So, what are these matrices? So, this matrix Q is nothing but a stacking of all the eigenvectors. So, V1 all the way up to Vn. Okay. And usually since there is a scaling ambiguity in this equation that you see above, that we choose the eigenvector such that the eigenvector itself is a unit vector, which means that if I take the L2 norm of V1, Vi, that is going to be 1, which means if I take each element of V1, square it up, add it up and take the square root, I will get 1. So that basically takes into account the ambiguity by the scaling factor. So now your eigenvalue is defined in a standard way, where the eigenvector is a unit vector. Now if you take a set of eigenvectors and stack them up and make a matrix Q, the other property is that Vi, its dot product with Vj, is going to be delta Ij. What is delta Ij? That delta Ij means that delta Ij is equal to 0 when I is not equal to j, and is equal to 1 when I is equal to j. Okay. So the equal to part basically is described here, but the second part where I and j are different, that means that these two vectors are going to be orthogonal to each other in n dimensional space. And when you have a set of orthogonal vectors that form this matrix, its inverse is simply the transpose of the same matrix. Now what is interesting about this matrix lambda is that it is a diagonal matrix where all elements other than the diagonal elements are 0, and the diagonal elements are precisely this eigen values, which is lambda 1, lambda 2 all the way up to lambda n. All the other elements are 0. Off diagonal elements are all 0. So we talked about scalars, we talked about vectors, we talked about matrices. Now let's talk about tensors, which are going to be useful in defining larger scale organization of numbers. So when we talk about scalars, so let's say you have a scalar alpha, it belongs to the set of real numbers. Then we have vector x that belongs to the set of real numbers to the power n, but in general n cross 1, we can simply say to the power n. And then you have a matrix capital Y, this belongs to r to the power m cross n. Okay. Now we will have a tensor T. We will take this organization of 0 dimension, basically a single number, stack of numbers in 1 dimension, a stack of number in a 2-dimensional array to nth dimensional array. So here you can have m cross n cross p or even larger set of dimensions. So you can think of these numbers that are organized in rows, columns, and then depth, and perhaps higher dimensions which I cannot describe and it is hard to imagine, but it could be in higher dimensions also. So T belongs to r to the power m cross n cross etc. Okay, q etc. It could be like a larger set of numbers. So now let us say if I want to define the transpose of this, so I have to take the transpose, okay, of T, then I cannot simply swap the rows and columns because I have rows, columns and other dimensions. So I have to define the new order in which these dimensions will be rearranged. So I have to define, so let us say if it was 4 dimensions, if it had 4 different dimensions, then I have to define how those are reordered. So if they were 0, 1, 2 and 3, I would have to define that the new dimensions would be, the third dimension would now come first, the the first dimension now would not change place, second dimension will not change place, but the 0th dimension and the third dimension have changed places. So, from 0, 1, 2, 3, that was the original set of indices of the dimensions. Now, it has become 3, 1, 2, 0. If you had only 2, 0, 1, then the only swapping that you can do is 1, 0. That is why we did not need to specify the order when we were talking about matrices, because there was only m and n and we can only swap them when we reorder. But here when we do the reordering, we have to specify the order in which the reordering will happen. Now, let us talk about functions. So, let us say you have a function f that is a mapping from set x to set y. Okay. So, let us say we have an element x that belongs to set x, okay. Then f of x will belong to y, and we say that y is equal to f of x, okay, and this belongs to capital Y. So, it is a many to one mapping. Many x's can map to the same y, okay. But if we have a function, if we have an expression like this, so an example of a function would be that y is equal to ax square plus bx plus c, which is the equation of a parabola. You can see that, let us say this is the equation of the parabola, this is your x axis, this is your y axis. You can see that two x's can give you the same y, but the same y can give you, so it is a many to one mapping. But if you have something like this, that x square plus y square is equal to 1, which means that y is equal to plus minus square root of 1 minus x square. Now, you have two values of y. So, this is not a function, not a function. So, function has to have a one unique value when you plug in x in it. So, when we look at these functions, we can define some characteristics of these functions, such as their continuity, their derivative, etc. So, let us first look at continuity and then we will look at the derivative. So, continuous functions are those that do not have jumps. So, simply put, that if we have limit of delta x tending to 0, okay, f of x plus delta x is equal to f of x. If this condition is satisfied for all x, then it is a continuous function. Now, in terms of limits, the next thing that is defined is the derivative of the function. So, we will define it as f dash of x. This would be limit of delta x tending to 0, f x plus delta x minus f x and divided by delta x. So, in general, if this is your f of x and this is x and then this is the function, then at any point the derivative is the slope. So, here the slope is positive, here the slope is negative. So, the tan of the angle of the tangent is the slope, and that is defined by this derivative. Now, you can have functions that are continuous, but their derivative is not continuous. So, for example, if I take a function which is like this here and then suddenly it goes like this, you can see that the function is continuous, but at this point the derivative is not defined. Okay. on the left hand side the derivative is 0, on the right hand side of this point the derivative is 1, but at that point the derivative is not defined. But we will talk about something else, that is a set of these lines that stay below this that can graze this point, right. So, for all these points there are different slopes, and as long as we pick a slope such that this line stays below the curve at this point, then what we can say is that these set of lines are called not tangents but subtangents, and their set of slopes is called subgradient. So, sometimes we will use this property when we are studying machine learning, that the subgradient of this function is defined everywhere. Now, there are points where f dash is 0. So, let us say if you have, let us say if f dash x is equal to 0, that means the function becomes flat locally at a particular point. That leads to something called a critical point. Now, there are different types of critical points. So, let us say if we are looking at f of x, you can have a point like here where the slope is 0. This is a minima critical point. You can have a point that is a local maxima critical point, or you can simply have something that becomes flat and then goes up again. So, this particular point is a inflection point. So, there are different types of critical points. The difference between minimas, maximas and inflection points is that we will have to go to the second derivative, which is the derivative of the derivative. Okay. Now, this second derivative in terms of minima is positive when you have a local minima, which means that the slope was negative here, but it is increasing when you go towards the right hand side. So, it goes from negative to positive, whereas in maxima it goes from positive to negative. So, f double dash x is less than 0, and at point of inflection f double dash x is equal to 0. So, greater than 0 leads to minima, less than 0 leads to maxima, and equal to 0 leads to inflection point. With after defining the derivatives and critical points, now we will look at an algorithm to find the maxima or a minima of a continuous function. So, let us say we have a continuous function, okay, and we are at some point here. Okay. So, this is x, this is f of x, and what we want is we want to find this minima. Okay. We want to find the value of x star that gives me the minimum point. Okay. So, here what is the direction with which I should change x? So, you can see that x star lies to the left of x, and if by some chance I had x here, then you can see that x star lies to the right of x. So, how can we find this direction? If you look at the slope here, this slope is positive and x star lies in the negative direction, whereas here the slope is negative and x star lies in the positive direction. So, if I want to find the minima, I want to go in I want to descend the gradient, I want to go opposite to the gradient. On the other hand, if I want to find a maxima, here if I start x here, I can see that x star lies on the positive side and the slope here is also positive, whereas here the slope is negative and x star also lies on the negative side. So, for finding minimas I want to do gradient descent, and for finding maximas I want to do gradient ascent. So, this gives me a recipe to find minimas. So, the minima finding algorithm is simply iterate or repeat until, okay, and within this loop I will have x new is x old, okay, minus some small constant eta times f dash of x, okay, and then x old becomes same as x new. And until, let us say the f dash x, its mod is less than epsilon. Okay. So, that means I have reached here where the slope is very close to 0. So, what does this critical step x old minus eta times f dash x means? So, here what I am saying is that this is your x old and I know that the slope is positive. So, I am taking a small factor eta times this slope and subtracting it. So, now I have taken a step to the left, okay, and this is my new position of x, this is my x new, and then I simply replace x old, the x new becomes x old, then I keep taking such small steps and hopefully towards the end after some iterations I will reach the minima. Now, when is this useful? If you have a simple function such as f x is equal to a x square plus b x plus c, then you can analytically find the minima, right, as minus b by 2a. But that is not what we are talking about. Many times this f of x is an unknown function in the sense that, or sorry, not an unknown function, but it is a complicated function. It has many terms and we do not want to, we can't find the minima using simple analytical methods, but we can compute its derivative. So, if we can compute its derivative, we can use this algorithm to update x iteratively until we reach the minima. Now, there is a critical element eta which is called the step size or learning rate. So, this step size can be neither too large nor too small. If it is too small, I will need many steps to go through this loop to reach the minima. If eta is too large, then my update is going to be so large that I can increase f of x instead of decreasing f of x. So, as long as I don't, as long as I keep decreasing f of x, I can keep the eta between, eta has to be smaller than a certain number. So, this eta is a positive number, but it cannot be very large. If I have a simple second order polynomial, then I can have exact eta calculation, and that basically is f f dash of x divided by f double dash of x, and that is called Newton's method. But we will see when we talk about machine learning that this is not very useful. So, we stick to this gradient descent where we only compute the first order derivative of x, of f of x. Now, let us talk about multivariate functions. So, sometimes you have functions of more than one variable. So, let us say you have y is equal to f of x1 and x2. Okay. An example of this could be something like a x1 square plus b x2 square. Okay. So, let us say this is the function. So, now when we take the derivative of y with respect to x, we will have to basically take derivative with respect to x1 and derivative with respect to x2 by holding the other one constant. So, basically now instead of derivative, so we will define something called gradient of y. So, gradient of y is a vector and the dimension of the vector is the number of variables that you have in the function. So, this is going to be partial derivative of y with respect to x1 and partial derivative of y with respect to x2. So, what is this going to be? This is going to be 2a x1 and 2a x2. Okay. So, how do we visualize these functions? So, I cannot draw in 2 dimensions, but let us say you have a plane of x1 and x2. So, now y would be if I take values of if I take the locus of those x1 x2 locations where y is constant, then I will get from this equation I will get ellipses, right. So, I will get these contours. So, this is one ellipse, then this is another ellipse. So, what is happening on this ellipse? On these ellipses the value of y is constant, the ax1 square plus bx2 square is constant. And now what is this gradient? That if I take any x1 x2 point, okay. So, here now this is a vector, this vector points to a direction, okay. It points to a direction which is normal to the tangent at this contour. This direction is the direction of fastest ascent. If you go in this direction a unit distance or not a unit distance, but an infinitesimal distance, and that the magnitude of that step is constant, then in any other direction you will not increase y as much as if you were to go in this direction. So, this direction is the normal to the tangent at that contour, and it is given by 2a x1 and 2b x2. So, now if I want to do gradient descent in 2 dimensions, okay, then basically what I will say is that my x1 x2 has to be updated such that it is the old x1 x2 minus eta times gradient of y. What is gradient of y? For this particular function, this is the gradient of y. So, this is also a 2-dimensional vector, x itself is a 2-dimensional vector. So, all the dimensions check out. So, we will make use of this algorithm for multivariate optimization. So, now let us look at maximas and minimas of multivariate functions. So, again if we go back to that x1 x2 example and we simply take ax1 square plus bx2 square and we assume a and b both are greater than 0. So, we get contours like this, all right. And here we know that the minima is at the origin. So, that this critical point which is the minima is represented by gradient of, so let us say if this is y, then gradient of y is equal to 0, which means both dimensions of the gradient are going to be 0. So, which means that 2a x1 and 2b y x2 are both 0. okay, which means that both x1 and x2 are 0. That's how we land up at the origin. Now, on the other hand, if we have a and b as both negative, then this condition that the gradient is 0 will define a maxima. So, your maxima will be at the origin, and for both of these points the gradient is 0. Now, in 2 dimensions something interesting happens, that you could have, for example, a greater than 0 and b less than 0, in which case you will have maxima in one direction and minima in another direction. So, this implies at origin is a maxima for x2 direction and minima for x1 direction. Okay. So, this is called a saddle point. So, what is a saddle point? Think of a saddle. So, let us say you are sitting on a horse. Okay. You are sitting on a horse, and just below you is a saddle point, where if you look at your front and back, you are at the minima, but if you look at your left and right, you are at a maxima. So, you are a maxima from left to right, but front to back you are at a minima. So, here you have second derivative which is different, which is positive and negative for the 2 directions. It has different sign for both directions. Now, let's switch gears and we will talk about probability. And the basic concept in probability is that of a random variable. So, let's say we have a variable x. Okay. So, this variable can take different values, and the value cannot be predetermined. It's not a predetermined value, it's a random value. However, it's not as random as the name suggests. It can still follow a probability distribution where some values are more likely than other values. So, let's say we have a random variable x and it can take some value which is small x. So, we will use this notation. And to give you a concrete example, let's say we are looking at a coin toss which can take value either heads or tails. So, the event space that we will have is H and T. So, what is an event space? Event space is a mutually exclusive and collectively exhaustive set of values that a random variable can take. So, which means that if I add up the probability of all the values, possible values that the random variable can take, it will add up to 1, and the probability of each particular value will be greater than 0. Okay, so, this is a discrete random variable where the values come from a discrete set, such as this one, which is head and tail. Now, when we work with random variables, it is customary to assign these discrete values some numbers, and that assignment is rather arbitrary. So, what we will say is that this value x can belong to this set which is 0, 1, where we have mapped head to 0 and tails to 1. So, now if we look at a coin toss, this coin can have a cross section that is that has the same face on the head side and the same face on the tail side. If that is the case, then it is a fair coin, in the sense that if I toss it, the probability of it landing on its head versus landing on its tail is the same. So, what we will say is that probability that x has value 0 is equal to 1 minus the probability that x has value 1, and in this case this is going to be 0.5 for a fair coin. If the coin is biased, perhaps the cross section has a slightly larger face for one of the outcomes and slightly smaller face for the other outcome, In that case, the probability of x being 0 need not be 0.5, it can be greater or less than 0.5, but it will always be between 0 and 1. Okay. So, what we will say is that for all x, okay, the probability that the random variable x takes this value x is going to be greater than equal to 0, all right, and sum over all x, the probability that this random variable takes the value x is going to add up to 1. Okay. So, with this we are ready to define what is the probability mass function. So, a probability mass function would basically be a functional representation of these probabilities. So, on the x axis I have discrete categories. So, let us say I have 0 and 1, and then I have on the y axis I have probability that x takes this value x. So, here the x axis is x. So, here let us say this is not a fair coin and one of these values is 0.6 and the other value is 0.4. So, this is a probability mass function. At each point there is a mass of probability that is associated with that, or another way to write this would be that we just show these Dirac delta functions with 0.6 and 0.4 if we were to make this space a continuous space in X. That means there is no outcome which is between 0 and 1, but usually for discrete outcomes we stick to a bar graph. We do not want to use this Dirac delta function which is associated with continuous variables. Here we do not have a continuous variable. Now, the other thing is that I can convert, if I had a continuous variable, I could convert this into a CDF, which is a cumulative mass function or cumulative distribution function. In which case your y axis is probability that x has value less than equal to x, and we have x here. So, we will see a rise in probability to 0.6 at 0, and then we will see another rise with a, so this is 0.6, and then we will see another rise of 0.4 which will lead to a total height of 1, and this rise will come at 1. So, this is a discontinuous function, and if we were to erroneously represent x as a continuous variable, then the graph of cumulative distribution would look like this. By cumulative I mean we are adding all the probabilities of all the events that all the values that are below that value of x. Similarly, if we have a 6-faced dice, right, and this dice can, let us say it is a fair dice, then all the values from 1 to 6 are equally likely. Its probability mass function is going to look like this. So, let us say I now map the numbers directly to 1, 2, 3, 4, 5 and 6. Then I will have this rising up to 1 by 6, 1 by 6, 1 by 6, 1 by 6 and 1 by 6. Okay. Let us look at some common probability mass functions. The first one is inspired from this coin toss, which is for a binary variable, and this is called a Bernoulli distribution. Okay. So, here x belongs to this discrete set 0 and 1, all right, and we define a parameter of this distribution which is mu. Mu is the probability that x takes the value 1. And the distribution, which we will write as BERN, okay, and we will have x given mu, all right. So, this vertical line is given. This probability is going to be mu to the power x 1 minus mu to the power 1 minus x. So, this particular form of this function is very important. So, you want to pay attention to this. So, you can see that this power x is either 0 or 1. It cannot take any value between 0 or 1 or outside of 0 or 1. It has to be either 0 or 1. So, if you see this power, if it is 1, that means the Bernoulli distribution is just mu. The distribution value or the probability mass function value is just mu. On the other hand, if x is 0, then this mu to the power 0 becomes 1, which means that it has no effect, and what we get is 1 minus mu to the power 1 minus x, which is going to be where x is 0, we will get 1 minus mu. So, this is basically a selection between mu and 1 minus mu. Okay. If x is equal to 1, if x is equal to 0. So, selecting between two binary values is very easy if your power is a binary variable, and you can use these power as x and 1 minus x, and you can multiply the two. This is a common mathematical trick that we will encounter later in the course. So, now with any distribution, what we can also define is the expected value of any function. So, let us say expected value of x. Okay. So, what is the expected value of x? Expected value of x is sum over all values of x, okay. And then we have x probability x is equal to x. Now, if we evaluate this, what we will get is that the expected value of x is going to be mu. So, similarly, we can evaluate the variance in x. So, that would be the expected value of x minus x bar, where x bar is the expected value of x whole squared. Okay. So, that will come out to be, so basically your expected value of that will come out to be mu times 1 minus mu. Okay. So, keep in mind that if you want to evaluate the expected value of any function, so if you have expected value of f of x, okay, that is nothing but sum over the all values of x, f of x times p of x is equal to small x. So, this can be used to compute the variance, this can be used to compute the mean, etc. A related distribution to the Bernoulli distribution is the binomial distribution. So, in Bernoulli distribution, what we were talking about was a single coin toss, and what is the outcome of that. Now, let us assume that we do n coin tosses, and out of that we want to see from 0 to n how many times. So, let us say we pick the number of heads, we want to see between 0 and n how many times the head comes, and then what is the distribution of that. So basically we will call this as binomial distribution of, now I will change the variable y, given what is the probability of landing on its head for a single coin toss, which is mu, okay, and the number of coin tosses, which is n. All right. So this binomial distribution is, as you might expect, n choose y, mu to the power y, 1 minus mu to the power 1 minus y. So this is the binomial distribution, and its event space is going to be 0 to n. So its graph is going to be from 0 to n and all the numbers in between. Okay. And it is going to have bars here, a bar here, and then a bar here, a bar here, a bar here, a bar here, and so forth. All these bars will add up to 1, because that's from the definition of the probability mass function. Okay. So similarly, we can compute the expected value of x, we can compute the variance of, expected value of y, we can compute the variance of y, etc., using this formula that we have seen here. Now, if you have more than one variable, then we can define something called joint probability, conditional probability, and marginal probability. So let's take the example of a dice, and in this dice we define, based on this dice we define two variables. Okay. So first let's take the basic variable, which is x, and this belongs to all the outcomes, which is 1, 2 of a single roll, 1, 2, 3, 4, 5 and 6. But then let's define y, okay, as the event that the one of these 6 numbers that comes up is an even number. So this will be a binary variable, 0, 1, where 0 implies even and 1 implies odd. Let's define another binary variable, which is z. This also has value either 0 or 1, and this takes the value 0 if x is less than 3. If we roll the dice and we get a number 1 or 2, then x is 0. If we get 3, 4, 5 or 6, then x is 1. Okay. So now for these two variables, we have a joint probability distribution. Okay. And this distribution is going to be a two-dimensional array, where you will have rows for outcomes of z and columns for outcome of y, or vice versa. So let's take this, and here I will use y for rows. So we have y is equal to 0, y is equal to 1, z is equal to 0, z is equal to 1. Okay. And we know that the outcome that z is 0 and y is 0, which means that we will get an even number and it will be less than 3, is only one even number, which is 2. So this is going to be 1 by 6. All right. And then again that the number is less than 3, but it is odd, which is going to be only one number. If we get 1, so that is 1 by 6. The probability is 1 by 6. On the other hand, if we have if we get a number greater than or equal to 3, but it is even, then it can be 4 or 6. So the probability is 2 by 6 or 1 by 3. And similarly, this probability is also 2 by 6 or 1 by 3. So here by definition, this distribution will have all entries that will be greater than equal to 0. So, this will always be greater than equal to 0. Additionally, if I sum it over all values of y, all values of z, then pyz will sum up to 1. Now, let us look at two additional concepts, which is conditional probability and marginal probability. This is the basic joint distribution. This is joint distribution. And now let's look at conditional. So, let us say we want to define P of y given z. Now, z has to take a particular value, it cannot just remain a variable. So, what that means is that we will have to choose the value of z to be one of the values in the event space of z, which is going to be either 0 or 1. So, let us pick the value where z is even, okay, and so let us take the value Pz is equal to 0, but before that the formula for P of y given z is P of y comma z divided by P of z from Bayes theorem. So, now where does this P of z come from? This P of z comes from something called marginal distribution. All right. So, P of z is going to be sum over all values of y. We are going to eliminate y. Okay. P of y comma z. Similarly, P of y is going to be sum over all values of z, P of y comma z. So, now let us look at what that looks like. So, let us say if we were to fix the value of, let us say we take the value of z is equal to 0. So, what is the probability that z is equal to 0? Which means that what is the probability that when we roll the dice, the number will be less than 3. So, obviously that has to be 2 by 6, which is the probability of getting either a 1 or a 2. So, now where does this come from? If we come back to this table for the joint distribution, so we are summing over all possible values of y, which means y is equal to 0 and y is equal to 1. So, if we add these up, if we add these up, what we will get is 1 by 6 plus 1 by 6, which is 1 by 3. Here we will get, if we add these up, we will get 2 by 3. And on the other hand, if we add up the row, we will get we will get 1 by 2 and 1 by 2. Okay. So, basically this particular column is P of y, this particular row is P of z. Okay. So, this is the marginal distribution. So, now based on that we can define the conditional distribution. So, what is P of y given z is equal to 0? So, if we know that the number is less than the number is less than 3, then what is the probability that we got an even number versus versus the probability that we got an odd number. So, let us look at the even number. So, let us look at P of y equal to 0. Okay. So, P of y equal to 0 given z is equal to 0 is going to be the joint distribution that both of them are 0, which is 1 by 6 divided by P of z is equal to 0, which we know here to be 1 by 3. So, this is half. Okay. So, similarly we can find other conditional distributions by using Bayes theorem. So, until now we talked about discrete random variables. Now, let us switch gears and talk about continuous random variables. So, let us say we have a variable x and it can take any value x. So, if it is a continuous random variable, let us take an example of heights of people in a particular course, and we line up all the students by the height, and we are looking at exactly the value of x is equal to 170 centimeter. Now there is going to be no one in the class who will have height of exactly 170 centimeter. Some of them may be slightly below 170, some of them may be slightly above 170, but 170 is a very precise number, and usually if you have a continuous variable, you do not get a very precise value. You cannot have any measurement that will be exactly on a decided precise value. So this probability is usually going to be 0, okay. But strictly speaking, it is actually greater than equal to 0. So it is greater than equal to 0, but then I integrate it, okay. So this is a probability density function. So if I just look at exactly for one value, it is going to be 0, but I define something called small p, which is a probability density function. So this density function, this need not be 0. So this is the probability of, this is the density of the probability. Basically it tells you relatively in an infinitesimally small interval around x, what is the likelihood of x taking the value inside that interval versus some other interval. So what this means is that you have a graph that you have where you have x on the x axis, and then you have p of x on the y axis, and the area under the entire curve is 1. So integration of p of x dx is equal to 1, and p of x itself is going to be greater than equal to 0. Okay. Now what is the probability of x taking a value between some interval a and b? So that is basically the area that is between these two limits a and b. So probability that a is less than x less than equal to b is equal to integral from a to b px dx. So this is the definition of the density function. So for a continuous random variable. Okay. So now if we look at these continuous curves, what is the value that a variable takes a precise value? So that will be a very small interval. Because the interval is so small, then that probability is going to be 0. A related quantity that we have with this is called cumulative density. Cumulative density function, and that is the integral of minus infinity to 2a of px dx. So now here let us say I have the variable a, and this function, the cumulative CDF, will be a non-decreasing function, which will be 0 at minus infinity, and it will saturate at 1. Okay, so it is nothing but the left integral of the probability density function. Now the same CDF, if you remember, for a discrete random variable was a something like a stepwise approximation of this continuous curve. So that is one way to think about the relation between discrete and continuous probability distributions. Let's take a look at a very common probability density function, which is the Gaussian or the normal distribution. So here the symbol that is used is a stylized n for normal, x, and this is defined by two parameters, a mu and a sigma. Okay. So, if we look at x on the x axis, this will take a bell shaped curve. The tip of that bell will be at mu, and a measure of its spread would be sigma. So, this is the formula for this is 1 by 2 pi sigma square root, okay, e to the power minus x minus mu whole square divided by 2 sigma square. Okay. So, this particular formula gives you this bell shaped curve, and it is a very commonly used distribution because it rises naturally in many natural phenomena when you have an aggregation of many small parts. Each of them have their own distribution, but their sum will start to have a Gaussian distribution. So, we will call the expected value of x to be so we will evaluate this as what we had earlier as a sum. Now instead of that we will have an integral of minus infinity to infinity, okay, x px dx. What is px? Px is precisely this formula that was given above, and for Gaussian distribution this comes out to be mu, and the expected value of x minus mu whole square is precisely sigma square in the case of Gaussian distribution. So, the Gaussian distribution, the two parameters are the mean and the variance itself. Another distribution, for just to give you another example, is a beta distribution, and here your x will not lie from minus infinity to plus infinity, but it will lie between 0 and 1. So, x belongs to 0 1 interval, okay, and here it is given as beta distribution of x given two parameters a and b, all right. And the formula is that it is going to be gamma function of a plus b divided by gamma of a, gamma of b, and then x to the power a minus 1, 1 minus x to the power b minus 1. So, this is and this is for x belonging to between a and b. Another useful function is the uniform distribution. Again, it has two parameters a and b, and its graph can be something like this, that you have x here and you have from a to b you have a constant height, and that height is 1 by b minus a, so that the area under it is integrates to 1. Okay. So, just like we saw multiple variables in the discrete form, you can also have multiple variables in the continuous form. So, let us say you have two variables x1 and x2. So, you can have a joint distribution over x1 and x2. Now, I cannot draw this joint distribution, but I can draw its contours. So, let us say if I have axis x1 and I have axis x2, I can draw the contours of equal density where perhaps this is the maximum density and then it tapers off as I go further away from this point, and this could be a representation of a joint distribution. So, here this will always be greater than equal to 0, and if I take its double integral from minus infinity to infinity of p of x1 x2 dx1 dx2, guess what it will be? This will be 1. So, just like we had marginal distribution and conditional distributions, we will have marginal distribution here as well. So, if I take this distribution px1 px2 px1 x2 and I integrate it over dx1, then I will get the marginal over x2 and vice versa. And if I want a conditional, so p of x2 given that x1 takes a value a is going to be, again by Bayes theorem, p of x1 is equal to a comma x2, whatever value x2 takes, divided by the density p of x1 is equal to a. The last thing that we will talk about is an example of a multivariate continuous distribution, and here we will talk about the multivariate Gaussian distribution. So, let us say you have a variable x which is x1 and x2. So, the graphical representation of this Gaussian distribution would be that you have, let us say, two axes x1 and x2, and somewhere you have a mean value or expected value, and then you have these elliptical contours of the density function, the p x1 x2. If I take any slice of it, or if I take any projection and integral of it, those slices will look like Gaussian in one dimension, but right now I have two dimensions. So, basically this p of, let us call it x. So, this p of x, which is a two dimensional variable, is going to be, or multi-dimensional variable in general, is going to be 1 by 2 pi to the power k. K is the dimension. So, this could be 2 in this case, but it could be more, it could be 3 also if you have a 3-dimensional variable, and then determinant of the covariance matrix, this entire thing will be under a square root, and this basically evaluates to the single dimensional Gaussian if k was equal to 1, and then we will have e to the power minus 1 by 2 x minus mu transpose. Now, x is a vector because it has k dimension, and then covariance matrix inverse x minus mu. So, what is this mu? What is this sigma? Okay. So, mu itself you can see needs a mu1 and a mu2. So, mu itself is a vector which is represented by mu1 and mu2, or mu1, mu2, mu3 up to mu k. So, that is why x minus mu is a vector and we can take its transpose, and your sigma is going to be a square matrix of size k by k. So, this will be sigma 1 1 square, sigma 1 2, sigma 2 1 and sigma 2 2 square. So, what is sigma 1 1, sigma 1 2, sigma 2 1 and sigma 2 square. Sigma, so first of all it's a symmetric matrix, which means that sigma 1 2 and sigma 2 1 are the same. These are expected values of, this is basically a cross correlation matrix. So the diagonal elements are the variance of the same variable of a single variable, whereas the off diagonal terms are covariance of pairwise variables. So if your off diagonal terms are 0, then these ellipses are going to be aligned to the axis. If the off diagonal terms are not 0, then these ellipses are going to be tilted. So that's a way to think about it. And the center of these ellipses, which is the highest probability density, is going to be at mu 1, mu 2, or up to mu k. With this we come to the end of mathematics for machine learning, and I hope you will have a solid foundation when you actually go into machine learning models after mastering these mathematical concepts. Thank you.